All right, last speaker is Collin Kovacs, and he'll be presenting fast and frugal memory search for communication.
Alrighty, let me share my screen. The slideshow. Okay, can everyone hear me? I'm assuming you can. Okay, I don't see anything. All right. Hi, everybody. My name is Collin Kovacs. I'm a recent master's graduate from Indiana University. I had the privilege of working with Abhilasha the past year and Jasper as well on our paper, Fast and Frugal Memory Search for Communication. So I'll give you some introduction and motivation as to what we wrote about. So our motivation here is how does search and retrieval occur within communicative contexts? In other words, do individuals choose the best utterance or communicate the first utterance? And what we mean by utterance is some sort of communicative action that you would take in some sort of communicative scenario, whatever that be. Previous work has found that speakers generate optimal utterances when multiple concepts need to be identified. An example of a concept in this case would be semantic difference, which is actually something that we study in this paper, but it's understanding the difference between two words through some sort of semantic similarity. When trying to understand those concepts, reference games have been used to understand the utterances and the communication preferences. And a reference game that would be used is Connector, which this current study examines in detail. So what is Connector? So if anyone has ever played the board game Codenames, it's a very similar process. It's very similar board, in how it's a 20 word board and it's 5 by 4 words, 5 by 4 board of words. But in this game, we tell a guesser and a speaker, we tell just the speaker the word pair. And we tell the speaker to generate one clue that is not from this given board. So in this example, the speaker generates the clue medieval for the word pair cave and night. And note that cave and night are on the board. So then the guesser is then told to generate 2 guesses based off of the speaker clue that was given. So medieval, and the guesser has to give 2 words from the board that would semantically correlate to medieval. So in this case, the guesser gave knight and Robin, and we see that that's not correct. So this would be an incorrect trial. In this case, since they only got knight right, but didn't get cave right and put Robin instead. So this leads to a problem of not understanding how they were able to come to those final clues and final guesses. We have no way of understanding the generation process. So in this study, we told them to generate 3 to 8 clue candidates that they think would be good for their respective scenarios. So the speaker in this case gave 4 different words that they felt would be good as clues for cave and night. So they gave hidden, medieval, hunt, and bear, and then eventually narrowed it down to medieval. And note that they were allowed to give any sort of word that actually was not part of their clue candidate, which will come up later on. The guesser had a similar process where they were allowed to generate 3 to 8 words from the clue that the speaker gave from the board. So the guesser in this case gave knight, firm, robin, sunny, and tree. So 5 different words from the board, to which they narrowed down to knight and robin, which obviously wasn't correct based off of the previous example. But we can see that we are now able to understand the generation process of what led them to come up with their final guesses and final clues. So given that introduction, we're going to look at the method as to how we used that board game and the participants in the procedure for this experiment. We're going to look at the results from this, especially the effectiveness of manipulation when it comes to these final candidates. We're going to look at the response selection of what these are and the semantic search analysis, which will become more clear once I get there. And eventually the discussion to kind of go more in depth about what we will see. So let's talk about the method. So we used 53 pairs of people, so in total 106 people. And the game was conducted online, so no in person, all done over a computer that Jesper created. And the participants played 30 rounds across 10 boards with 3 word pairs in varying difficulty. I'll give an example here. So take the previous board that we used, and we can see that in this case, so green is obviously easy, yellow is medium, and red would be hard. So in this case, the green easy word pair would be oak and tree, since they're not too semantically different. The quick and glow were the medium, and cave and night ended up being the hard word pair. So we were able to evaluate whether the speaker listener exhibited patterns of selection. And we were able to define difficulty over these word pairs based off of like similarity techniques based off of embeddings from the small world of words and different data sets like that. So let's talk about some results from this experiment. So some performance across the tasks. So in this visualization, we compare the 2 studies. So the original study was using the previous connector board where that had no candidate generation, and the candidate study, which is this current study, which uses the candidate generation. The 3 words on the visualization is the first 2 are the word pair, and the final word is the final clue that was selected over time for all the trials. Oh, whoops. So the red is the optimal pairing, and the gold is the empirical fit. So for example, the happy, sad, emotion, for the word pair, happy and sad, emotion was given as a final clue about 80% of the time across all trials. So luckily there was no bias between the 2 studies, and we're able to continue on with this by applying a linear mixed effects model against the 2 data sets for the 2 different studies, and show that they're not dissimilar in any way. So we're able to evaluate that. So now we can look at the effectiveness of the manipulation of words here in candidates. So we wanted to examine if typing the candidates affected the response time. So in the first study, when generating their final clues, they had to type in their clues rather than select them on a computer. And we can see that this heavily affected the response time when generating the final clues, because they could have thought this initially and then just selected or wrote down whatever they liked. But in this case, they were able to produce the clue right off the bat in the candidate study. But for guessers, it was a similar amount of response time, since we're able to quickly just click what they thought and go on about their way when generating their different candidates and guesses for the word pairs. So now on, we're going to only refer to the candidate study, not the original study that was done. So in this case, when looking at the clue candidates, so that's what's on the x-axis here, we see that typically for generating clues, the first clue candidate that came to the speaker was the first thing that they selected across all difficulties. And this is where I mentioned previously where the none comes into effect here. Right here at the end, because they could have selected a clue that was not a part of their candidates. So we see that for the generating clues that they selected the first candidate that came to mind as what they felt to be the most correct one. And similarly, guessers took a similar action. So the first two candidates that they came up with as guesses became their word pair. And it's pretty significant because this came up about more than 50% of the time based off these plots across similar difficulties. And it shows that obviously that they were more likely to take their first thought than consider later candidates that they have posited. So now we can look at the selection from these responses. So using these graphs here, we can see that over the difficulty, it's actually more significant to select a later candidate rather than the first candidate. So we can see in easy scenarios, like happy and sad, then it was more optimal to select the first candidate instead rather than the later candidate. But you can see as difficulty increases over time, it was actually more optimal to select the later candidate, which implies this: take the first strategy, which was not optimal, obviously, even though it was the most popular. And this was assumed to be that individuals are used to reasoning with easier concepts. Usually when we deal with harder concepts, we would like to break them down into easier parts that we feel actually work into our benefit. So when dealing with only hard concepts or medium to hard concepts, it was not always the first thing that worked was the best. So now we can talk about this semantic search analysis and what this truly means. So we're trying to understand the types of candidates that the speakers are producing. So the ones that are producing the clues for the guessers to produce the word pair. So we constructed these things called patches. And these patches are the unique first candidates for the given word pair across all participants. So every trial, the speaker would generate their 3 to 8 candidates, and the first candidate that was given was then grouped across all participants for all word pairs for all trials. And then that was then used to create a patch of consistent of these unique first candidates. So for example, a patch would be very small if every speaker produced similar first candidates, which we'll see here. So for the given patch of happy and sad, the size is only 5. So we can see that most people over time produced a very similar first candidate that we saw in the proportion visualization earlier, where 80% of the time the participants used emotions as their first clue and final clue. But we can see as it increases in difficulty to medium, that the size actually increases as well. And it continues on with a harder one that we found in the previous board, which is Cave and Night, and that the size is actually 26. So we then were able to evaluate this movement or this transitioning that we defined as these 4 characteristics here: in, out, out, and out, in. Essentially, in is if a word moves to another word inside the patch, then is an in transition. So the words in bold here are the clue candidates that were given for a certain trial. And hidden here is the first clue candidate that was given. So obviously it classified into each transition at the trial level in 4 different types. And we can see that it moves relatively inside the patch, but then eventually moves out from there. And then they eventually selected medieval to be their final clue, which brought them back into the patch. So what does this all mean, and how does it relate to what we're actually doing here? So what we wanted to understand is the transitions of correct trials and incorrect trials. So we eventually found that correct trials had more in transitions and incorrect trials had more out transitions, which essentially leads us to believe that straying away from the patch of initial candidates led to unsolved trials, which relates back to the optimal solution of the take the first strategy, that we're referring to earlier. So let's talk more about what our results actually mean in this context. So we can do a little recap here. So players typically selected the first candidate, like we said, even though later candidates were more accurate, which indicates that take the first strategy. And again, that take the first strategy is the first thing you thought of, was the first thing that it must be right, essentially. So even though we saw that it wasn't actually true for later samples, participants actually believe this to be true. So the participants responded with potential candidates as they came to mind. And we want to understand whether this was the true candidate that they were thinking of or not. So we want to understand through some sort of eye movement tracker if this might provide some key to validating the participants' potential candidates. So for example, they could be looking at a certain word in the board, but actually choose to, select something else based on kind of taking a step back and looking at the board to see if this is actually true. And then we want to see if the speakers actually pay attention to the board at all, to see, when they're given the word pair, do they just look around, they just think to be what could be true, without even taking context of what the actual board is saying. And for guessers to determine whether eye movements align with verbal utterances as well. So pretty similar to what I was saying about, are they just going to think of the words first and then go back down onto the board level and see what is actually true, what's the most similar thing to them, and what makes sense. So we can eventually explore about how the candidates are generated, essentially. So we can use these through different models like GPT-3 or BERT, or we can use different algorithms like random walks that can be used to help validate more of the transitional periods or the semantic choices for the actual word pairs and things like that. Okay. All right. Thank you. So any questions, let me know.
Hi. Thanks for the talk.
Hi. Yep.
I'm not sure whether I just didn't understand this, but so you said like in some cases the later generated options were better, and I take that as like better, like semantically closer. But what if the generator and the guesser have sort of the same bias, like they have the same first intuition, like then it would be better, like not like optimally, like for the word embedding, but like the first option generated might still be the best in terms of like having the other person guess it. If we just have the same sort of, if we start in the same sort of semantics area, right? Like, I'm not sure whether that makes sense.
I'm trying to follow. I don't think I understand completely, but I think to an extent, where it did for easier word pairs, yeah, it was always the optimal choice of providing the first thing that you saw. So in that case, I think it would be okay. But we did see that over time, as the difficulty increases, that was not always the case. So I don't know if that helps.
Sorry, optimal here is optimal
Yes.
in terms of what is guessed by the guesser, or optimal in terms of what is like semantically a good word to sort of pair the two?
Okay. Yeah. So optimal in this case would be referring to the generated word pair by the guesser and to see if that was correct or not. And to
Sure.
also provide a very good semantic clue for the guesser as well. So optimal in both senses. Yeah.
All right. Thanks.
Yeah, of course. Yeah. Thank you.
If there's no questions from the chat, then I think we're good to go. Thank you everyone for attending the session.
Thank you.